All right, so now that we've been talking about hit testing and basically what it is and what the general problem is, I'm going to dig in a little bit and talk about how do we test, actually testing for a hit. Now, in the simple case, this isn't so bad. Of course, again, once you're in the same space, same coordinate system. If you're not in the same coordinate system, it doesn't really make any sense. You need to be in the same coordinate system. You just test the point P. For example, mouse position, for example. If the shape you're testing against is a rectangle, it's really easy. And we've seen this before in our example. It's this case up here where, I have my mouse and I click and I want to test against this green rectangle. Again, if they're in the same space, same coordinate system, all I do is to check if the left of the rectangle is less than point X value, which is less than the right. And if the top, for example, is less than point Y, which is less than bottom. This is, of course, assuming that top is a smaller number going down. Depending on the coordinate system, you might need to swap those top and bottom, of less than or greater than, that kind of thing. So rectangle is really simple. If it's within left and right and it's within top and the bottom, you're within the rectangle. Very quick. A circle actually turns out to be really easy as well. All that you do is you compare the distance between the mouse and the center of the circle with the radius. So first we go, okay, well the distance is the circle center minus P, so the difference there. It doesn't matter what order you put them in, you'll see why in a because distances are actually positive always. We don't have negative distances. Where am I? Yeah, so you imagine we have a circle here, and you have a pointer, and you want to go, no, if you clicked within that circle, come on. Yeah, I'm a little confused here. Shouldn't be distance. Maybe it should be delta. That's what confused me. Yeah, so the delta is the difference between the circle center and the point you have. And again, the order doesn't matter because when we convert it to a distance, no matter what order you do it in, you'll get the exact same distance because distance is a positive quantity. And then what you do is you just compare delta x squared plus delta y squared. Okay, now you should be realizing that I need to square root that, and I want to compare that against my radius because that's the formula for distance between 2 points. But I can actually get rid of that square root and square both sides. Square roots are slow, so I compare x squared plus y squared to r squared, and so it's a lot faster. And this is the short version of, or the long version of, distance is less than radius. And I'll write that in my notes to square both sides to avoid square root, because square roots are slow. Cool, so that's easy. Rectangle, circle. Triangle is the next one I want to talk about. So we have a triangle down here, and you have your mouse, and you click, am I inside the triangle? Well, we've actually learned how to do this, right? This is just our point and triangle test. And since this comes up so often, this might be a good time to go back and look at the notes if you've forgotten how that works. And this was covered in Unit 2. Okay. So far so good. We've also covered, very briefly, but we've covered convex polygon. And if the polygon is convex, like in this case here, then it actually turns out to be almost identical to the point and triangle test. You just check the cross products if they're all in the same direction. If I'm to the clockwise direction of all these edges, then I'm inside any convex polygon. So it's really easy. Generalized point in triangle. test, right? Basically the same thing. And the last one I'll briefly mention is concave or complex polygons. And you can go back to that section, and if you recall from that section, I don't like polygons, turn them into triangles, do that, pre-process it as much as you can, and just things get simpler. But it's worth talking about. If I have and I'm clicking against the complex polygon, we have learned how to do this. Even odd parity rule, for example, or the non-zero winding rule. So this actually covers most things that we'll come across. Most of it will actually come down to either a circle or a triangle, actually, with rectangles being very convenient for bounding volumes. And so I would say for the most part, you'll just have to do this when you're doing hit testing in 2D, okay? So now's a good time. I actually want to bring up a sketch to go over an example here. And I actually had a lot of fun with this. Here we are. I should actually update the size so it's a little more legible for everybody. All right. So here we go. So this is a simple program. I have an array of triangles. Okay, we have triangles, and then each triangle has 3 points. Each point has an x and a y, so it's a three-dimensional array. I just have a variable here. I can set 30 triangles. And then what we've done is we've set up some transformations. And this is some translation, some rotation, some scaling. Forget animation for a second, actually. I should probably turn that off. We'll come back to it. So then when we create our program, all that we do is we set up our ortho, -1 to 1, so we have an NDC coordinate system that we're working in. And then, this is an annoying processing thing. If we're drawing 2D in 3D mode, there are some accelerations that make it go funny. Where they overlap, you can get some problems, kind of like Z fighting, but it's not quite. So we just turn off the optimizations. We tell them we're doing 2D mode, okay? So I go through all my triangles. I give it a new random location within NDC. That's good. And then what happens is, with these other ones, translate, rotate, and scale, each triangle gets its own. So you have a triangle with its own random spot in object coordinates, but then what we do is we apply a random translation to it, a random rotate to it, and a random scale to it. So we create our triangles in object space, and then we come up with some transformations. Each triangle gets a translate, a rotate, and a scale, which creates a unique triangle on the screen. I'll come back to this transforms in a bit. And this is our animation. I'll come back to that. It's cool. And then when I draw my program, all that I do is I go through every triangle in my list and I draw it. And then if I look at my draw triangle, we reset to identity matrix, we translate our triangle, we rotate it, and we scale based on those random. So every triangle will be different. And then we're actually going to learn how to pick it, how to point at it, and we'll actually draw it with a different color if we figure out which triangle we're pointing at. Okay. And then we draw the triangle here. We begin shape triangles and we draw it. So basically, each triangle has a random shape within its own space, and then we do some random transformations to it. The reason I did this, instead of just having a random triangle in the screen, is because this is more realistic of what you're going to do in a scene. You're going to have some shape in its own coordinate system, but then you're going to have some transformations that you apply to it before you draw it. In that case, we still need to do hit testing, okay? So what I've actually done here is after we apply our translate, our rotate, or scale, and this could be any number of transforms, it doesn't matter. After you apply all your transforms, what I've done is I actually ask the OpenGL driver for the resulting matrix, and I save it. I'm like, okay, what matrix did we use to draw this? Because we're going to use it later when we do picking to make sure everything's in the same coordinate space. Okay, so this is the basic program where we draw each triangle. Let's take a look at what it looks like so far. So we have 30 random triangles. Every time I run it, we'll get something different. Some are overlapping, some are not. No big deal. Some are degenerate, or nearly degenerate, or degenerate. It's going to happen with random triangles, right? Okay. So what we are doing now, we have this set up where we have 30 triangles. We want to pick it. We want to click on the screen and find out, hey, are we overlapping? Are we inside a triangle? So let's go down to mouse pressed. When the mouse is pressed, we go through all the stages we talked about. So like we said in the notes, you need to work in the same space. Either bring all the vertices into the screen or somehow. The first thing I do is I convert the mouse coordinates into NDC. This is just a ratio explained in the notes. So mouse is going to be from -1 to 1, -1 to 1. So we're in NDC. So good. I've converted the mouse to NDC. Here's some debugging stuff. I'm assuming I have no hit. I'm assuming I haven't hit anybody. And then what I have to do, when I click the mouse button, I actually have to go through every single triangle in the list. I go through every single triangle in the list and go, hey, did we overlap with you? Did we overlap with you? Did we overlap with you? Okay, we have to check every single one. And I have a short circuit here, right? If we find one, let's stop looking, okay? That's all that is. So if we found a triangle that we're overlapped with, let's stop looking. So what do we do? So we have a mouse in NDC. We could bring the mouse all the way down to object space for each triangle, but what I've decided to do here is we transform each triangle also into NDC. And the way we do it is we take the triangle x coordinate, this is first vertex, second vertex, and third vertex of the triangle. And what I've done is I've taken the transform that I saved earlier that we used to draw the triangle, and this is saved up here. You might want to watch this a second time if you're not following. When we actually draw the triangle, we translate, rotate, and scale, and then we save it. Save transform for later. And then we draw. So I have this transform matrix that brought the object from its object coordinate system to the screen. Actually, not the screen, but the normalized device coordinates because of our ortho, -1 to 1. I saved that matrix. I use the exact same transformation down here myself on the 3 vertices of the triangle. So the graphics card does it to draw it. I need to do it again because I'm going to use it for my point and triangle test. So I convert every triangle vertex into normalized device coordinates, bam, and then I use point and triangle, my 3 triangle vertices, against my mouse in NDC. So I bring the mouse from viewport into NDC, the triangles from object space into NDC. Now we're in the same space. Now we can do point and triangle test. This is a lot of work. So you might be thinking there must be a better way to optimize this. Well, you can get tricks, and there are clever ways to do it. The reality is we only need to do this when I click, not 60 times a second like drawing. So it might not make sense to save those points if the graphics card is doing it anyway every time. That memory load might be higher than occasionally doing it when I click the mouse button. It's different in a game sometimes where you're doing hit testing live. Even then you might be able to get away with a lower frame rate, or if it really needed, you could try optimizing at that time. So we transform the triangle into NDC, great. And then the mouse is in NDC. Now we can just call point and triangle, which we've learned before, with those 3 triangle vertices and the mouse. And then if it tells me it's true, I save which one it hit. Maybe I'll print that out. I hit which triangle number, and that's just the index in the array. The other thing to note here is we're doing it in reverse order. We start from the last triangle and go to the first. And that might seem kind of weird, but it's just a trick to make sure that we select the top triangle. If triangles are overlapping, I'm drawing from top to bottom, right? If you look at my draw loop up here, we're drawing from the 0 all the way to the end, right? That triangle 0 all the way to the end. Bam, bam, bam. So the last triangle will be on top. So when I do hit testing, I go into reverse order. Okay, the last drawn one I'll check, and if I have a hit, I won't match the triangle underneath it. So you do these little tricks to make sure you keep the right order, and you'll see how that works when I run it. So I'm going to run this, and the program runs just like normal. And now what I can do, I can click, and I'm not hitting anything, but if I click this triangle, then what's going to happen is this is going to get true. The hit will change to the triangle number, and when it draws, it'll draw a different color. Just like that. I click out, see? So you can select triangles. Where it gets interesting is this case here, where there are 2 triangles below me, but because we're checking in reverse order of drawing, we'll match the front one first, and we'll stop checking. Okay? So we can actually do that. It's really neat. And you could imagine turning this into a drag and drop, or you could do all kinds of really cool things with this. I can select which triangle I want. Great. Now the last thing I wanted to do here, I turned it off, is animation. But before I do that, I want to show this. I actually include some code to show how we can bring the mouse all the way into object space. Now remember, we talked about if you have a robot or something, or a model, and you want to figure out where the person clicked in that model, sometimes it's useful to have that click point in object space. So if you want to do that, you can just get your transform, you can invert it, because the transform goes from object space all the way to NDC. Our mouse is in NDC already. We can invert that, right? So we can go all the way to object space, and you can do the exact same code. This works, but the inversion is expensive, so this solution up above is quicker. So we do all these transforms on 6 transforms for the 6 coordinate, like 3 points, x and y each. And then point and triangle should be no surprise. We generate the edge vectors, we check the cross products, okay? And then we check them like that. So we check our cross product for our point and triangle test, and we're done. So that's really nice. And then we have a cross product. Okay, so no surprises here, but it's a lot to get working. And especially after the transform unit, you can see now that understanding different coordinate systems and moving freely between them is what you need to be able to do to solve these problems. So I'm going to run this. Oh, we already ran it. Next thing was animation. The reason I wanted it to animate is that I want you to see how we're doing this live. We can't pre-process things. In a real scene, things are moving, and you can't pre-process all the locations and whatnot, because they might be moving or the camera might be moving. So in addition to all the object locations, I've also added a move, like an X and a Y, which direction it's moving and how fast, and also a spin, how much it's turning. And so what we'll do is, I'm going to turn this back on, and then the amount that it's turning and the amount that it's moving will change. And it won't rotate in spot because we scale first, then we rotate, and then we translate. So you're going to get some funny, it's not going to rotate around the center of the object. So that's okay. But because we save that transform every time we draw, and then we use that to bring our triangle points in the same space as the mouth, this is robust, right? It's robust. And even as it's moving, it continues to work. So if you solve it in the general case, it really scales well to dynamic programs and whatnot like that. So this is kind of neat. I recommend downloading it and making sure you understand the code. It's a really good example for helping you move between coordinate systems. All right, that's a good spot to stop. That was demo number 8. That's a good spot to stop. I'm going to come back and we'll look at a different one. Thanks.